fancy things. High tech. It's not for me. All right. Okay, so yes, let's go back to what we had started last time, the day before yesterday, and put things into a certain order, because I'm afraid every time some new concepts are introduced, the students used to get lost from time to time, to a certain degree and to a certain extent, nevertheless. So once again, what we are considering, first of all, we are considering at the moment a one-dimensional system. So there is an x-axis and nothing else, which means that our space is one-dimensional Euclidean space. So don't think of a string, of a chain, which can vibrate in all directions. This is not what I mean. I mean that the space is purely and solely one-dimensional. There is no transverse direction whatsoever. It's a model, of course. We're trying to describe something which is pertinent to any dimensional system, but the simplest way to do it is to consider just one-dimensional problem. We have coordinates for the atoms which live on this line. We know them by x1, x2, and so forth, xn. N is the total number of particles. Whatever is our Hamiltonian, we will assume that the simplest way to do it is to assume that the number of particles is finite. It is of course very large, but it's finite. And to make life easier and consistent, you have to impose some boundary conditions. The simplest and most straightforward boundary conditions are periodic boundary conditions, or Born-Karman, as you know. Which means that if I have n plus L, this is the same as L. Which means that the endpoints of my systems are glued together. So the n plus first and the first atom are just the same atoms. And in fact, the manifold which I obtain in this way, the space, is no longer, strictly speaking, mathematically speaking, is no longer a Euclidean one-dimensional space. It's a circle. It's a compact space, which is different from Euclidean space, which cannot be described by a variable which varies within the finite interval. If you want to describe points on a circle, what you do, you fix the location of the center, you draw the radius, and you determine the orientation by an angle. And the angle varies from 0 to 2 pi. It's a finite interval. This is a feature of all compact manifolds, like a sphere, for instance. So we intentionally replace the open, so to speak, unbounded one-dimensional Euclidean space by a bounded circle, because in this way it is easier to do calculations, to do Fourier transforms and things like this. Right? Now about the Hamiltonian. So we have endpoints and material points. Each point, all of them are equivalent, identical. They have the same mass, m. So therefore, the total energy is a sum of the kinetic energy and some potential energy. So the first thing we do, we impose the requirement that the system has to be translational invariant, translationary invariant. If we keep in mind that what we have done is just this, not this, but this, translation invariant translates to arbitrary rotations, as you can see, of this wave that you're seeing. the car and the rotating. It's precisely the same thing, right? So you're making a shift along the line is equivalent to rotating by a certain angle. The only thing is that when I'm talking about global translations, if I assume that xn is replaced by xn plus some quantity x large, this x large is the same for all indices n, for all particles, all of them simultaneously and by the same amount are shifted either to the right or to the left by the quantity which is x. Which translates to saying that all of the particles, the whole system, is rotated to the right, clockwise or counterclockwise by a certain angle. Just the same, at the same language. So you have to keep in mind just your line is bended and transformed to a circle. Oh. Now the most important requirement is, of course, is translation invariant. Translation invariance. What I mean by that? That for all n simultaneously, by an arbitrary amount x, I make the set of transformations in the Hamiltonian, and the Hamiltonian does not change. This is what is meant by translation invariance. There is nothing to discuss here, because here we have, roughly speaking, Dirac derivative of the coordinates, x dot squared. It's velocities, right? Momentum. So whatever is the shift, it doesn't affect the velocity. But here we have a serious thing, because if the potential energy is invariant under this global transformation, this means that the potential U cannot depend on x1 or x2 or xn independently. This is not allowed. What is allowed is that x, the U, has to be a function which depends on all possible differences, xa minus xj. Because only for this difference, shifting the coordinate doesn't affect the function. That's the usual things. If you have a function of two coordinates or two variables, and you see, I have some kind of invariance under the shift, under translation. The immediate consequence is you can't depend on the center of gravity of the 2 points. You should depend only on the relative coordinate. Because shifting as a whole, if it's costly, that means that your invariance is lost. Okay, so this is what very, very important consequence in this case for whatever happens next. It's just this one. This is fine. And then you ask the question, what happens if you minimize your potential U? And when you minimize your potential U, you assume that you have done this. You performed all the calculations, and you know it's the explicit form of U, which follows this prescription. And then it turns out that I have to obtain some equilibrium configuration. I have to fix the values of all the coordinates, x1, x2. So what I want to minimize. I want to minimize the potential energy. I find the configuration which gives the minimum to the total energy of the system. Right? That's exactly the problem I'm addressing. The natural question is, how am I going to measure my coordinates? I have already started doing this without emphasizing what I've done. What I've done is somewhere here or there or on the Pluto or on some Mars, somewhere in the universe, there is a reference frame once and forever. And I measure all the distances, all the coordinates in that reference frame. There is something out there, independent of my will. I measure So I have a very elementary device I can measure. So in other words, what I have an absolute axis, so to speak, the absolute reference frame, which is stat. I measure everything with respect to it. And then the answer is, what I'm going to obtain is a crystal. It's a periodic alignment of my atoms with some interatomic spacing, A0, which can be derived after minimizing the potential. It's a microscopic. You have sit down and work it out. Right. So how should I parameterize it? I write down that the equilibrium value of the coordinate is n times A0, and n takes values 1, 2, 3, and so forth and such. Is it correct? The question is, I insist that this cannot be correct. This is correct, but this is not the whole story. This doesn't cover all the solutions. It's only one of the solutions. Why? Because again, what is written below in the line is fixed. This line has its own, digits. 1 centimeter, 2 centimeters, 3 centimeters, and so forth. How will I put this lattice onto that line? It depends on me. Therefore, here I should put this B. Of course, B should be restricted within this interval. Why? Because if B has reached A0, if B is shifted, it gives me a shift by Y0, I simply relabel my indices. I replaced n by n plus 1, and that's all. That means that whether I put 1, 2, 3 like this, or I put n here, 1 here, 2 here, and 3 there. So this is the same configuration. Using the periodic boundary conditions, just the way you label your sites, that will be just the same. So therefore, it's quite sufficient to have B to be quite accurate. Let's put greater or equal to 0, but strictly less than A0. Because B is equal to A0 is the same as B is equal to 0. That's it. Right. Which means that, in fact, we've got not one, but a continuum of solutions. The continuum is parameterized by a continuous parameter B, which varies between 0 and A0. And any such solution is fine, is okay. Always a crystal. It's a crystalline structure, which may be shifted with respect to its location by an arbitrary amount. But since it occurs due to the shift, and since we have full translation invariance, global translation invariance, which is this, when x is arbitrary, therefore the ground state or the energy of this configuration should not depend on B. That's an interesting thing. So the ground state, the minimal energy state, is degenerate, is infinitely degenerate. There is a parameter, continuous parameter varying between 0 and A0, which parameterizes different ground states. Each ground state is different from the other. If you, for instance, were thinking quantum mechanically and built up wave functions for different value of B, so suppose that you do all the quantum mechanical calculations. So you know the solution of the Schrödinger equation and you know the wave function for n-particle state, ground state, right? And of course this ground state will be parameterized by B, and you consider the wave function for the parameter B and the wave function for the parameter B prime. And they calculate the overlap, the scalar product of those. In the limit when n goes to 0, you would obtain the Kronecker delta BB prime. It's sufficient for B not to be equal B prime exactly in the limit of infinitely large number of particles, the overlap is 0. These two states are orthogonal. This is one of the fundamental statements one can make. What I'm talking about actually is the basics of Goldstone theory, if you wish. So good. So the ground states, therefore by ground state, you can assume the quantum mechanical ground state, or you can assume a classical minimal energy state, whatever I can parameterize by B. And I know that if I shift this state by amount x, this is the abbreviation for the action. X goes to x large. It's a translation operator. This is x large. Then this TXB is not B. Instead, it is something like B prime, which is not equal to B. Translations generate different vacua, different ground states. And there is infinite amount of those. The ground state is degenerate. The symmetry, the true symmetry of the system, since the system, the minimal energy state represents a lattice, the only degree of freedom I'm left with is translations by A naught, by the lattice spacing, all the multiple of lattice spacings. So the symmetry not of the Hamiltonian, the symmetry of the state, the symmetry of the lattice per se, is lower than the symmetry of free empty space. It is not translation invariant, because acting on this, by this, on any ground state, I get a new state, not the original one, which has suffered, because I make a shift. Right? So the symmetry is lower than it was before, because the original Hamiltonian was symmetric under any translations, any global translations. The state, which is the minimal energy state, right, has lower symmetry. It's only invariant under discrete translations by a certain amount. So the original symmetry, the full symmetry, turns out to be broken in the ground state. And this is a spontaneous breakdown of the symmetry, without participating of any external potentials. Please notice, your potential energy only depends on the relative distance between the particles. There is no external potential which affects, the energies of individual particles. This is the example which has been raised, the question has been raised of one of your colleagues the day before yesterday. A very good question. So that's precisely what the whole story is about. And now we refer to good textbooks on statistical physics or field theory, which tell us that, number one, if the symmetry is continuous, symmetry must be continuous. This is fulfilled because the symmetry we're discussing is translational symmetry. It's parameterized by any parameter x changing from minus infinity to plus infinity. If the symmetry is continuous, and if the symmetry is spontaneously broken, this means that the symmetry is lowered, roughly speaking. It's not as high as it was. For instance, you might have a different physical system which would be invariant under arbitrary rotations in three-dimensional space, and then in the end of the day, some specific direction, like in ferromagnets, would be fixed. That will be a spontaneous magnetization. All the rotation which is left over are plane rotations around the axis fixed by magnetization. Then what you will say, the O3 symmetry is replaced now by planar O2 symmetry. O3 symmetry was the symmetry of the Hamiltonian. O2 symmetry is the symmetry of the ground state, which is lower. And again, you would say, this condition is satisfied, yes sir, and this also satisfied. So we have broken this symmetry. The system itself breaks its symmetry in the ground state, and the new symmetry is not simply the previous one. It is not a continuous symmetry at all. It's a discrete symmetry. Of course, it's smaller. And then if these two conditions are satisfied, I have to add some other features. I would say perhaps the time reversal should be there, inversion symmetry should be there. Because then it turns out that at low energies, or in the continuum limit, the system all of a sudden displays new emergent properties such as Lorentz invariance. We are talking about our original problem is essentially non-relativistic, and there is no degrees of freedom which would be described in terms of the particles moving with the speed of light. Of course, nothing like that. The velocity is the group velocity existing in the condensed matter, but the structure of the equations displays some Lorentz group, Lorentz features. So if these two conditions are satisfied with some extra comments, what you have the Goldstone theory. And that theorem tells you you have to have necessarily, a low energy collective modes in the system called Goldstone bosons. The statistics is also predetermined. It cannot be a fermion, it's a boson. Such that the dispersion omega of k of these collective modes is such that its frequency goes to 0 when k goes to 0, which means when the wavelength of the corresponding excitations goes to infinity. In the long wavelength limit. We will clarify the physical meaning of this k equal to 0 mode just within 5 or 10 minutes. That's the essence of the theory. What I'm trying to tell you is, again, all what is behind all this story is translation invariance of your Hamiltonian. And the way it gets broken in the ground state, in the minimal energy state. Then it turns out that something that you know very well, the acoustic phonons are nothing but the Goldstone modes. They ought to be there. They have to be there. Not because you have calculated, you are so smart to be able to calculate them. No. It's for sure by itself, it's very important. But their presence is the consequence of something much more fundamental than the mere calculation. Don't underestimate it. This is what my message is, don't underestimate the essence of this effect, the appearance of acoustic vibrations in crystals. They follow from the very nature of crystals per se. Once nature arranges itself in the form of a periodic structure, the Goldstone modes or acoustic modes are there. Right. Okay. So let us now, therefore, after reminding our main points, which we started discussing last time, let us get back to our calculations, which we also had started last time. Perhaps I can erase this. Now I will go faster because we've done it already. we expand, we introduce the instantaneous time-dependent coordinate as its equilibrium value, which is this, and plus a displacement, u and t. And we assume that this displacement is much, much smaller than the interatomic distance, because interatomic distance is the only length scale, microscopic length scale, and all the rest should vibrate, should represent fluctuations small compared to this characteristic length scales. And therefore, u goes to its value at the minimal. I expand in powers of un, the linear terms is absent, we already discussed it, and then the quadratic correction looks like this. A and M is dynamical matrix, and plus higher order terms. About A and M, we know it's a real matrix, it's a symmetric matrix. Moreover, it depends on the difference. A and M is actually a function of the difference. That's fine. And now we materialize what we've said right now here. What we said? We said our model, our general model has a full translation invariance, which means that if I replace un by a constant, which is if I make a shift of the whole system as a whole, this is the global translation, then the energy is not going to change, because the delta U, all the un equal to epsilon minus u all the un equal to 0 is given by 1/2 epsilon squared double sum and m a. In view of this property, the requirement that the energy didn't change means that there is a certain rule, the sum rule, which tells me that a summation of over all the relative distances with both sides, signs taken into account, give you 0. So this is the property of the dynamical matrix, and this is nothing but the consequence of the global translation invariance. We have said that actually the existence of the Goldstone mode should follow from the translation invariance, so let's show it. Let us do this calculation. Let's do this calculation classically. When we do this calculation classically, we write down the equation, the Newton equation. This is the left-hand side, the standard one. In the right-hand side, you have the derivative, the force acting on the nth atom. So therefore, I differentiate with respect to m. And this gives me minus some sum over the latest sides, a and m, and u of m. This is a set of equations. The equations are linear, are very simple. This is the advantage of the harmonic approximation. I have to write down what is written here is the harmonic approximation. And in this harmonic approximation, well, the Hamiltonian turns out to be a quadratic form in terms of the displacements, and the equation of motion turned out to be linear, and therefore solvable, of course. The solution is found by turning to Fourier expansion. So here again, I recall I have my periodic boundary conditions. Everything is defined on the circle. Therefore, the theory is periodic in real space. And therefore, I can expand everything in normal modes, if you wish. It's a Fourier expansion. That's the essence of Fourier analysis, actually. We have to have periodic functions to be able to expand them in Fourier series. So you write down simply u of n is 1 over square root of n, it's normalization factor, k. You perform summations over k. I will comment on this. And the standard exponent. What is k? K, of course, is a certain set of allowed auxiliary real quantities. In the standard mechanics, without any hesitation, we call k is, of course, the momentum, what adds coordinates and momentum. But be careful. It's not that fast. The momenta are good quantum numbers in empty space, when full translation invariance is present. For a free particle in empty space, the momenta is a perfect quantum number. It's conserved. Here it is not. Once you are in the ground state, once you have formed the periodic crystal, your symmetry is no longer that of empty space. Your symmetry became discrete. As a consequence of this periodicity and discreteness, the momenta has disappeared. And you have to know that from band theory, from the standard band theory. Instead of momenta, you have this quasi-momentum, which varies in the finite interval. So there is a special Brillouin zone such that your momenta in this one-dimensional problem vary within the system. You know this, right? I don't have to. You do, right? I cannot hear the response. Well, some people sitting and no. Okay. All right. This is also, by the way, a closed manifold. The endpoints are glued together. It's not that just the interval k, and this is pi by a naught, 0, and this is minus pi by a naught. In fact, these 2 points are equivalent, and they're glued together. So the Brillouin zone is a circle, in fact. It's a topological manifold. This is why so much noise about topological insulator, topological superconductor, just because of the fact that the space when the wave functions, the block wave functions are defined, is compact. It's not like Euclidean space. It's not an open space, it's a compact space. Right. So it's k, therefore, is limited by the Brillouin zone, and I can do just the same for this matrix as a function of the relative coordinate. Again, I can write down 1 over, I don't remember whether n or maybe square root of n, doesn't matter much. I think it's a matter of normalization. Again, sum over k, a tilde of k, and the same exponent. So the essence of all this transformation is that if you rewrite in terms of the Fourier components, what you will obtain will be the same in the following equation. Qk double dot plus omega k squared qk is equal to 0. Such a beautiful set of equations where omega k squared is 1 over the mass, and here we have the Fourier transform a tilde of k of the dynamical matrix A, well, which will be 1 over n, sum over all L from 0, no, from over all L, A of L, and the exponent I minus AL A naught. So the outcome of all this hard work is is there an elementary equation describing for each particular k a harmonic oscillator? What can be simpler, either in the mechanics, classical mechanics, or quantum mechanics? It's the simplest and the most important problem whatsoever in whole physics. You eliminate this problem from classical or quantum mechanics, the life stops. You don't exist. You don't exist anymore. You're somewhere there. What is important? The most important thing is that if you look at this equation in the coordinate representation, you try to follow the displacement of the nth latest side, nth atom. And it turns out that you cannot close this equation because through the matrix A and M, through the dynamical matrix, UN couples to all other displacements, which is natural. It should have been like this, because if you perturb the latest somewhere by deviating a given atom at some point, the information would spread and affect the motion of some other, due to dynamical forces, right? So it's essentially, in real space, it's essentially a non-diagonal problem. And you want to diagonalize it. And that's exactly what you do. You do the Fourier transform, you do a unitary transformation, you change variables in a smart way, unitary transformation, because the number of particles should be conserved, the number of degrees of freedom should be conserved, nothing should be lost. You do this transformation, it's all these n are normalization factors, we'll discuss technicalities, it's not that important. What is important that different k's become disentangled, different pseudo momenta are independent. Now we have a superposition. So you see what happens. That's the explanation of what happens. This is how you represent the field, the displacement field. You expand it in all possible elementary harmonic waves. And each harmonic wave is described by Q of k, and Q of k plays the role of the coordinate of an oscillator whose frequency is omega of k, whose value is this. And the frequency is determined by the dynamical matrix. So you have solved the problem completely, and you are most happy people in the world. But you haven't shown the most important thing so far. What do you have to show? You have to show that even though we didn't specify the form of K of L, we must be able to demonstrate that the translational invariance immediately leads to the Goldstone theory, without any calculation, only following from the requirement, from the property of translation invariance. What was the translation invariance in our case? The translation invariance would tell us that if now I go to the limit k to 0, we all understand that if we have waves here, these waves are described by this exponent, and small k are associated with large wavelengths. So when k goes to 0, the wavelength of the corresponding wave, partial wave, goes to infinity. Right? What happens if k goes to 0? Then I have omega limit. When k goes to 0, omega of k squared, it's 1 over n. And here I lose this exponent. L takes all the values, and I have this matrix. Now, I think I have already erased it, because I'm trying to see it. To find it.
The one box there, the translational invariance, the sum over 1n, an.
Oh, here we are. We have shown to exist, this relation which has been shown to exist as a consequence of the total global invariance with respect to arbitrary translations. So you do show, you can show in this way that the value of the frequency at the infinite wavelength is what? Is zero. What does it mean? It means the following. Let us single out this value, k equal to 0. Imagine that in this expansion, I single out only the value k equal to 0. I'm interested in the role of this specific term. If I did that, I will obtain that un would be replaced by what? 1 over square root of n, and then the value of this q at k equal to 0. This is a number, this is a number. The whole expression is a constant, which does not depend on n. What is that? It's a uniform shift. So the wave, which has k equal to 0, describes a uniform shift. It's quite simple to understand, because if we draw a wave like this with some period, then at this maximum the displacement is maximum. It is 0 here. It starts increasing a little bit. Here it is decreases. Here it reaches 0 again. Then it starts going in the opposite direction. It becomes large in negative, and again, and then the whole process repeats. Now it's easy to understand that if the wavelength becomes infinite, then you have the shift of your atoms either to the left or the left, but this will not depend on at which atom you are looking. All of them will shift in the same way. So therefore, any wave, it's quite a general statement for any wave process. Any wave with infinite wavelength describes a uniform transformation. For the lattice, it will be a translation. For a magnet, it will be uniform rotation, and so forth and so on. So it's a uniform shift, and therefore, when you make a shift of your whole system by the same amount for the same atom, you simply change the ground state without affecting, without deforming it, and it costs you nothing. The energy you spend for that is 0. Because all these ground states are degenerate. There are no barriers separating them. Clear? I think it should be clear. Okay, now what we are left with is, what about small k dependence of the frequency? Well, what you do, you simply go to the limit of small k. The condition you impose is absolute value of k times a naught is much less than 1. What is that? The wavelength is much, much greater than a naught. Oh, that's a more interesting thing. You consider long waves like in the sea, in the ocean, you see. Huge scale. Very, very slow changes over large distances. You have to go very far to feel the difference between the levels of the shift or whatever. It's a large aggregates of your particles moving almost with the same phase to the right or to the left, and they cover huge distances. This is what long waves mean. Right? Small case, I have to expand this, and I can see that omega k squared is inverse mass. Here, first I will single out the term with L equal to 0, this A0. Again, I will have twice L positive strictly, AL, and times the cosine, KL A0. And now I will expand this cosine. One minus 1/2 KL E0 squared plus higher order terms. Now please notice, this plus twice this expression times 1 is precisely this. If I take k equal to 0, I'm left with this plus this. And this is exactly this. So therefore, this plus this term, they cancel each other. So what remains is omega k squared is 1 over m minus sign in front, A0 squared, k squared, sum over all positive L squared, AL squared. So the whole expression is proportional to k squared, and all the rest is grouped in the expression s squared times k squared, when s squared is minus A0 squared divided by the mass times the sum. From 0, L squared, AL. The claim is that S is nothing but the sum of velocity. S squared is a square. Now the first problem which arises when you look at this without any unbiased glance, how do we know that the sum is negative? So the minus side is positive. S squared must be positive. The squared must be positive just already because the negative value of the squares of the frequency are not allowed. Because if the frequency, square of the frequency is negative, then the frequency itself becomes imaginary. Now, since we have something like this, every time we have omega equal to plus minus I gamma, we have exponent minus plus gamma t. This is bad news. It would be very bad. It means that your solution wouldn't be stable. Your system would be unstable because either moving to the future or moving to the past. In dynamics and mechanics, both ways are legitimate. Unfortunately, in real life, they are not. You would have bad solutions, diverging solutions, which would be an indication that the state you started from, the ground state, is wrong. Your construction is wrong. This cannot be the case. In other words, there must be serious arguments proving that what is written here is strictly possible. And that's an exercise for you. You start thinking about it from now, anytime. So something like within a week, you together with some other problems, it will be one of the assignments. You have to. I'm not asking you to. Well, I'm not imposing any restrictions. Just bring about as plausible arguments as possible. Give yourself the right to come up with fantasies, whatever you wish. I want real hardcore arguments showing that this should be correct. So the conclusion, therefore, is when k goes to 0, the frequency of these excitations of this wave goes to zero linearly with some proportionality coefficient which is called the sound velocity. It's a linear dispersion. It's a linear dispersion. So it's something amazing. We start with the discrete model, the model of a discrete crystal. Then we encountered the importance of the symmetry, of the translational symmetry, and the way it gets broken spontaneously. We arrived at the structure of the crystal. Then we considered the long wavelength vibrations in such crystal. And what we obtained was a set of oscillators, each oscillator representing a collective mode with a certain dispersion, given by the frequency omega of k, such that when k goes to zero, then the wavelength of your collective excitations becomes extremely large. Your frequency goes to zero, it's number one. Number two, it goes linearly. And this is all, both facts constitute the essence of the Goldstone theory. So when you have such a linear dispersion, and I already said it's a sound wave, we have to have a few steps more, to show that the physics of the underlying physics indeed has to do with sound waves, with the continuous description of all underlying physics, even though we started from the discrete manifold our that is. So what I want to do now is to show again how profound was the Phil Anderson's idea about what he says, more is different. Let us make some progress and then we'll come back to discussions again. So lambda, the wavelength, is much greater than A naught. What is U of n? U of n is a discrete set of functions depending on time and labeled by the index n, which attribute the displacement to a particular point in space, particularly this side. But now, when you go to the limit of large, long wavelength, you have sufficiently large number of nearby located atoms whose phase in this process is nearly the same. In other words, if I look at the time dependence of this quantity and then I look at the time dependence of this quantity, or maybe this quantity, from n to n plus 1 to n plus 2, I will observe almost identical patterns, which means that discreteness is no longer an issue. Discreteness gets lost. Instead of a discrete manifold, a discrete set of variables un, we can introduce u of x, comma, when s is a continuous variable. Because from the point of view of this lambda, the discreteness of the lattice is not crucial. You remember what Phil was saying, Phil Anderson? There are certain properties, emerging properties, in the low energy limit, in the long wavelength limit, which are not sensitive with respect to the microscopic details of your system. Your lattice spacing and discreteness, it's a microscopic structure. The wave is characterized by parameters which are much larger. Therefore, this should be ignored completely, but it should be done smartly. In which way? In other words, u of nt is replaced by a function. What is then un? Okay. Okay, I forgot. I'm sorry. I had to stop at this point and simplify my life. And your too. Working with the most general dynamical matrix is it's a kind of editing, if you wish. We have shown something on very general terms, and but from practical purposes, it's sufficient to consider as simple model as possible. In other words, imagine that A of L is non-zero only for L equal to 0 and plus minus 1. So the coupling between the atoms doesn't spread on distances longer than the interatomic distances. There is a local term at equal to 0, and there are all nearest neighbors. If you do that, and you fine-tune the values A0, A plus minus 1 in such a way that this condition is satisfied, A0, in other words, A0 plus twice A1 must be 0. This should follow from this condition. Then the Hamiltonian, which we have, the kinetic energy is the same, but the potential energy becomes very, very simple. Un minus un plus 1. This is a coefficient k, which is called the spring constant, as you remember. And this is the difference between un and un plus 1. Only nearest neighbors interact. Further neighbors don't interact. And of course, the displacement must be taken in the square because we have a quadratic model and things like that. So what is this then? In the continuum limit, un minus un plus 1 is what? Is u of x minus ux plus a naught. But our distances are large compared to a naught. A naught for us is a microscopic tiny thing. So therefore we should expand this in the Fourier series. It will give us minus a naught du dx plus the correction of the a naught squared. Right? Good. Now, if I have some function, f of n, which is being summed over all n, under the condition that this function is smooth, which means fn minus fn plus 1, divided by the absolute value of fn, is much smaller than 1, is the relative change of the function is much smaller than its value at this point, right? Then this is a smooth function. And therefore, summation over n should be replaced, can be replaced by an integration. Of course, it should go to some integral from 0 to L dx. Is it all what I want? No, x is a distance. It has a dimensionality of length. And this f, whatever it has, it should be somewhere here. Instead of n, I simply write down x. But here I have to divide by a naught, because otherwise the two expressions will not have the same dimensionality. This should be dimensionless. And it's easy to figure out that you have to divide by the minimal distance to make sense. You have to think, if you remember the classical analysis in mathematics, how the Darboux sum are introduced when integral is derived. When you derive the notion of the integral, you start with summation, right? And then you go to the limiting procedure. And then we have delta n divided by delta x, and then you introduce the differential. This is exactly the way we proceed in the same way. we derive the integral if you wish. So this problem of lattice vibrations allows us to go back to our early years at the university. Right. Well, we are done, because everything is now looks fine. This quantity transforms to the second derivative of the displacement field. This quantity Pn is of course the mass times un dot. And therefore it will eventually transform to m and du xt dt. And this summation over n will transform to an integral. And all in all, what you will get will be the following model. Your Hamiltonian will have the following form. It will be the integral from 0 to L dx and the Hamiltonian density, where the Hamiltonian density is 1/2 rho du dt squared plus 1/2 t du dx squared, where rho is a linear mass density, and t, if I'm not mistaken, is the spring constant times a naught. It's what is called the linear tension. So you see, what is written here? It's the energy of an elastic string. So an elastic string, fixed by its end, ends 0 and L, is located somewhere along the line. You don't have any transverse motion. Everything what you have, it's a waves of compression. So your line, the density of your mass density undergoes vibrations along this line. And this is exactly what is described by this beautiful Hamiltonian. It's an elastic string which has a mass density, and has a tension. Once you deform it locally, you have to pay energy. This is exactly how much you pay when you don't change anything in time, but change it locally in space, compress, right? Or you may not change anything in space, but consider some kind of evolution. So locally at this very place, without moving from the point to point, at this very point, I have an increase in density or decreased density and something like this. Well, it's a well-known problem in mechanics. It's a string. It's an elastic string. I'm very sorry, our problem was not an elastic string. Our problem was a set of atoms forming a lattice. At the end of the day, from the point of view of long wavelength oscillations, we have an effective theory of string. And therefore, excitations in such a system are just acoustic waves, the standard sound waves. So therefore, your acoustic phonos are nothing but sound waves in the wavelength limit. Whatever is the exact dispersion of omega of k at small k, it is linearly proportional to k, with the proportionality coefficient being s. Right? So here again, I'm coming back to philosophy. You have to keep in mind what's going on. Right? This is the property which has emerged in the continuum limit. This was not incorporated in the very beginning, in the very structure of the Hamiltonian. The original Hamiltonian was perfectly discrete. It described set of points, set of coordinates, set of atoms. It's a discrete entities with some interaction between the atoms. That was something like this. in the end of the day, you forgot all this, and what you're left with is an elastic string. That's exactly what I'm saying again. What is the content of the Anderson's statement? There are emergent features which are as fundamental as any other. Please find out what are the characteristic parameters in this business. Is the density, which is expressed in terms of the mass, is the tension, which has a memory of the structure of the dynamical matrix. Well, you may say, where is the minimal distance in this problem, as we said, described last time? What is the minimal length scale? Of course, the minimal length scale is the latest basic. All the rest must be much larger than that. But we here obtain this result, very important result, with the description of the acoustic phonons in terms of the sound waves for free. We didn't work much, we didn't do anything, we didn't squeeze out the effective theory. Why? Because the model we were dealing with was elementary, absolutely simple. It was described by quadratic Hamiltonian. For quadratic Hamiltonian, for quadratic form, the spectrum is always additive in momentum K representation. So you have the spectrum, which is omega of K. If you were quantum, you would say the energy must look like something like this, perhaps. You would add a multiplier H, and then, if after some leap of thought, you would also introduce a quantum number, n of k, which takes integer values. It will be a quantization of the oscillator, and we will do that. But basically, this is the energy. And all what we need to know is the spectrum. And we know the spectrum. We can calculate for this model. For this model, we can do all the calculations exactly. And I will leave all this calculation to you. Please calculate exactly the spectrum of this specific quadratic model. I think you've done it millions of times already. Do it 1,000,001 and the first time, right? And then compare with our conclusion that again, I didn't say that, if I'm not mistaken, s squared must be t divided by rho, and then omega of k squared will go like s squared k squared for the sound waves. Yeah. So you simply go down by energy. You don't do anything with this part of higher energy part of the spectrum. It exists by itself because these different k don't talk to each other. Everything is factorized in terms of different k's. So the total energy is a sum of independent contributions from different k. In real life, it is not as simple. It turns out that some higher degrees of freedom non-trivially affect the low energy degrees of freedom, and you have to have enough skills to squeeze out from the total spectrum of the system the low energy, the infrared part, which you're interested in most of all. Here you don't need to work at all because it's a direct sum. Like you have a big bag, and which one do you want? The high energy, and it's for you, and the other one, low energy, it's for you. You don't have to work. It's already split, disentangled. But it's a property only of quadratic Hamiltonian, property of free theories. Free particles behave like this. So that's exactly what we have. And now I would like to come back to the question raised by this gentleman. What's your name, by the way? How shall I call you? EJ. Okay, fine. I would like to come back to this question because it's an interesting question. Well, how do we know that the Goldstone theorem is a consequence of the spontaneous breakdown of the symmetry, translational symmetry? What is the meaning of the word spontaneous? How can we anticipate the importance of being spontaneously broken? The suggestions coming from this gentleman last time was, what would happen if I had a potential, periodic potential, with the same period A naught? Well, generally speaking, it might have been with some other period, because I don't want to complicate the problem. Because when the periods of the potential and the one period which is incorporated here are not the same, you may have a very serious and very interesting problem to solve. But let's postpone it. Imagine that I have a substrate. You know what the substrate is, right? The system, a heavy system, like a plate, with some profile at the atomic level, which helps install the same periodicity here as it is dictated by the substrate itself. So in other words, in the ground state, what you do, you put all your system, all your atoms into the potential lens. Right. Now we have two effects. The atoms interact to each other, and this interaction is described by this. These are just springs which couple, say, nearest neighbor atoms. So every time you move one, it will affect the location of the other, of the neighbors. But on top of that, each of the atoms is located in its own potential well. Therefore, in the harmonic approximation again, in the same spirit, I may write down something like this: the mass omega naught squared divided by 2 times un squared. That's precisely what the gentleman had in mind. Let us add this to it. Because if I take a specific value of n, what I have, it's a parabolic potential for each atom. So the new lattice is replaced by a set of parabolic potentials, something like this. I don't care about the overlap at what I say. It's enough. For small vibrations, it's enough. So what is bad about all this? Who has an idea? What should we expect? We have described it, we discussed it briefly last time, but maybe you remember it. If you look at what is written here, what feature, what requirement is no longer satisfied? Which properties we have lost with this addition? Correct. We cannot now replace un by un plus some epsilon without paying a price. Here we can do that. Here we can't. In other words, if I look at what's going on, if I start pushing this atom from this equilibrium position, it will start climbing up either to the right or to the left. Up. And the energy will increase. Translation variance is lost. What I will obtain for the model in the continuum limit. You can write down almost blindly the effective Hamiltonian density will look like rho divided by 2 du dt squared plus s squared du dx squared. This is precisely what we had before. Here we have rho and here we have t. But I have pushed rho outside, and instead of t divided by rho is s squared. And believe me, your simple estimation will show you that all what would be added will be just this. The previous Hamiltonian did not depend on u. It depended only on the derivatives. So therefore, the previous Hamiltonian was invariant under shifting u. was not U dependent. It only depended on the derivatives. And now you got the dependence on U. It's a criminal action. You go to prison right away. You have broken translation invariance. And you have broken it explicitly. It's not like a spontaneous breakdown of translational symmetry in the ground state. You broke it explicitly. You, by hand, you added a term like this. And you said, okay, this is somewhere, it's a reference frame on Mars, on Jupiter. And now I cannot play this game with parameter B, which used to take value between those two limits. No, it is only a certain B which corresponds to the location of this atom just in that potential length. Say B equal to 0. That's it. So it's an explicitly broken symmetry. If you calculate the spectrum, omega of k, it will be S squared, k squared, plus omega naught squared. That's the answer. You know what's that? It's a massive boson. It's a boson, the solution of the Klein-Gordon equation. It's a Lorentz invariant object. It's a massive boson. How does it look like? Its spectrum in the beginning, omega as a function of k, let alone this pi divided by Neubrenner zone. We're not interested in the endpoints. We're working somewhere here for small k region. So what we had before was the standard sound. What we get now is this. And this distance is omega naught. And this is the mass, the relativistic mass, the relativistic, in quotes, mass of your boson. The Goldstone theorem doesn't work. You don't have a Goldstone particle. There is no particle with a linear spectrum. The particle has a mass. So you see why it happens like this. Because you broke the main rule. You broke explicitly translation invariance. It is allowed to be broken spontaneously due to the interaction between the atoms, but not due to the external potentials. You see? That's the important thing. Very important message. All right, so we still have some time, not much, but still have some time. Right. But maybe in the remaining time, I will briefly discuss the importance of what's going on. So when you have Hamiltonians like this, it may have to do with the lattices, it may have to do with magnetic systems, not exactly this, but some very similar. A discrete set of variables, the spins or atoms vibrating or rotating. What is written here when we call this is the Hamiltonian? So you are so much accustomed to Hamiltonians, maybe slightly less accustomed to Lagrangians, but Hamiltonians is fine. You measure simply the energy. You have a many-body system, many-particle system, and you have ingredients. You have particles labeled by coordinates or displacements of those coordinates, and you have the velocities of those particles or momenta if you wish. Then you may introduce quantum mechanical restrictions, you can introduce canonical commutation relations, whatever you want. But basically you have a set of variables. And then you impose the rules of the game. Okay, when this particle goes somewhere, it will affect the motion of some other particle, and this interaction is described by this term. If you have an energy scale, an energy axis at your disposal. And you have some characteristic energy which can be derived from here. Right? For instance, if you calculate the frequency of our vibrations, right? We are discussing the small k limit. But you can sit down and calculate, work out the general spectrum. And you will find out that the spectrum saturates close to the boundaries of the brilliant zone and then becomes periodic. Right? So you can estimate a typical value of this frequency at the boundaries. Actually, this is the maximum value. This is a typical value. Now, since you have energy, a typical energy, then you may ask yourself, if I have now temperature at my disposal, where should I expect the appearance of this beautiful collective phenomenon like what we're discussing, like Goldstone theorem, at high temperatures or at low temperatures? What do you think? In other words, these Hamiltonians which are written here, it's one of the examples. They describe what? The high energy physics or low energy physics? I'm asking you some kind of, in a sense, a stupid question, because we have been discussing the answer already both the day before yesterday and today. What do you think?
Low temperature, because the deviation U of n gets bigger and bigger as temperature rises, and
That's correct. That's correct. That's correct. Yes. You could even add a little bit more to this. That's correct. Of course, that's correct. Yes.
Because you are using the harmonic approximation.
Harmonic approximation. Well, okay. That's a good remark. If you raise temperature very, very strongly, the harmonic approximation would fail, and all the way your crystal will start melting. It will transform to a liquid. We are so far away from that bad scenario. No. We are still assuming that the harmonic approximation works. What I want to say that this remark was correct. The Hamiltonians, microscopic Hamiltonians with all the details, they're written one by line. The masses are these, the velocities are labeled by this, the currents are labeled by this. All the description is discrete. All the forces are known. All the potentials are known. All this has to do with the highest level possible energies. It's always highest energy physics. Why? Because at high energies, correlations between the particles disappear. Dynamical effects are negligible. Each particle appears as independent entity. And this is the starting point when we derive the Hamiltonian like this. We say, we have a particle, its momentum is Pn. We have a particle, its coordinate is Xn. What do we mean we have a particle? We assume that we have a particle. We may not have a particle. If you are in the regime of very low temperatures, you have waves, I'm sorry, you have collective excitations. There are no particles whatsoever. You have no right to think in terms of the particles. You have only waves. The notion of the particles is essentially a high energy or high temperature notion when correlations, dynamical correlations, are removed, and what remains only thermal fluctuations. In this, each particle appears as independent entities. Small, all the rest, all these things make sense because they can be taken into account using perturbation theory. They play a very tiny role. They cannot lead to any significant consequences. You can only estimate the tendency. Okay, if I switch on this interaction will affect the motion of a particular particle in this or that way. So therefore, everything what we have in mind, the most interesting part is what happens when the temperature, the energy is lowered. Then the interactions and correlations become increasingly important, and then you start losing information where you started from. The details are not as important as they used to be at high temperatures. Much less things remain and survive. This is very, very important to keep in mind. And just an example, you take this very problem, you take the problem of a vibrating lattice at high temperatures, where the correlations are neglected. You are left with individual atoms. They can move, they can vibrate, they don't go far away, maybe, but what you have is equipartition law. The energy per particle is of the order of kBt, and the specific heat is constant. Then you go to the lab, to your fellow practitioner, your friend, you drink coffee with him every day, and ask him to measure the specific heat of the sample, and he'll tell you that at low temperatures it follows the law T to the third, T cube. If the sample is non-metallic, it's contributed basically by lattice vibrations, T cube. You said classically a constant and T cube at low temperatures. How come? The phonons, these are just the acoustic phonons. These are just the effect of the collective gapless collective excitations. This is the effect of ghost storms. So what we are talking is not kind of, we want to make life beautiful. Of course, we do want to make life beautiful. But this is not the artificial attempt to make life beautiful, because it is not. No, it is indeed beautiful. All these properties don't come by randomly. They root in deep principle or conceptual statements based on very fundamental laws, such as symmetry, such as space dimensionality. So I will, maybe at some point, at some moment, we will stop discussing all these things with such intensity, but we will turn to real calculations. But these calculations, the day before yesterday and today, are quite simple, quite elementary. But in spite of their simplicity, they contain a lot of things to think about. So with this, I stop, and next time we'll be dealing with quantum description of the lattice, quantum effects. Now I push.